learned some things about rotation, and hopefully they've been interesting. So let's solidify it with an example. Way back when we started learning about rotation, I mentioned that it would help us understand how cats always land on their feet, even if they start their fall upside down. If you think about it, it's a bit weird. Say a cat falls off of something and at the top of the cat's fall, that's now, it's upside down and it has no angular momentum. There's no external torques acting on the cat when it's in the air, so its angular momentum has to stay zero while it's falling. But somehow, the cat manages to twist itself around and land on its feet. So, isn't the cat violating conservation of angular momentum? Because in order to twist it, it must have angular momentum, right? Before we start with the equations and numbers, let's be really sure to understand the theory and intuition of the problem. So, here's theory number 1. Cats supposedly have 9 lives, and that's got to violate some laws of physics, so maybe one more violation, no big deal. But, as opposed to the 9 lives myth, cat flipping is actually real. Check out this YouTube video if you don't believe it. It has nice slow motion footage of a cat flipping itself. And, okay, the 9 lives theory, not actually serious. On to theory number 2, gravity. Gravity is indeed an external force that acts on the falling cat, but gravity cannot create a net external torque on an object relative to its center of mass. So we're going to completely ignore gravity from now on, because in fact, gravity is not relevant to how the cat twists. Here's Ginger to help us with theory number 3. She's a cat, though she looks somewhat like a banana with a head taped on, and she has a beautiful stripe. These are Ginger's front paws and back paws. Ginger's starting out upside down, paws in the air. Now her front and back halves rotate in opposite directions. That means that even though Ginger is twisting, her front and back angular momentums cancel each other, keeping the total momentum zero at all times and, in fact, satisfying Mr. Isaac Newton. Now they've each rotated half a turn in opposite directions, and you can see that Ginger's right side up again. Go Ginger! Only problem, as you can see from her stripe, Ginger is very twisted. Real cats do not, cannot, and should not twist themselves into a corkscrew. Remember a few videos ago we mentioned that changing an object's shape can change its moment of inertia even without changing its mass. So when Ginger moves her front paws away from her body, her moment of inertia on her front half increases. So when she twists, in order to keep her front and back halves with equal and opposite angular momentum, her front has to spin more slowly than her back does. So her back twists a lot, and her front not so much. Next she retracts her front paws, stretches her back ones, and twists the other direction. This time her back moves slowly, and her front moves quickly. And Ginger lands gracefully paws down. Our banana cat has cleverly taken advantage of how angular momentum works. If that wasn't clear, here's another view. Ginger starts upside down, seen from the front, with her head, the front part of her body and paws in blue, and her rear in red. Her paws start facing up since she's upside down. Seen from the front, her back parts should be hidden behind her front ones, but I drew them displaced so you could see them. She starts rotating with her blue front rotating slowly clockwise and her red rear quickly counterclockwise. She keeps rotating that way until her rear has turned a bit more than half a turn. Then she reverses direction, tucks in her front legs and extends her rear, and spins the other way till she winds up head up and legs down. Now that we thoroughly understand the problem, let's do the numbers. We'll simplify Ginger's anatomy. Her front and back are each just a tube. She has no head. Each tube is 10 centimeters diameter and weighs 2 kilograms. Each tube has 2 paws attached to it, of which I've only drawn one. Each paw weighs half a kilogram and can either be tucked next to Ginger's body or stretched to be 10 centimeters away if she wants. I drew her front paw stretched. Let's start with some moments of inertia. The inertia of a tube about its long axis is I equals 1/2 mr squared, which comes out to 0.0025 kilogram meters squared here. We'll treat a paw as a point mass, either 5 or 15 centimeters from the central axis. The formula here is mr squared. A radius of 5 centimeters for a tucked-in paw gives us half a kilogram times 0.05 meters squared, or 0.00125 kilogram meters squared, and a stretched out paw gives us 0.01125 kilogram meters squared. Next, we'll sum up the inertia of Ginger's entire front half, one tube and two stretched out paws, remembering that the inertia of an object is just the sum of the inertias of its parts. So 0.0025 and twice 0.01125 gives us 0.025 kilogram meters squared for the front half. Ginger's back half has its paws in, giving a lower inertia of 0.005 kilogram meters squared. Next, we'll compute the angular acceleration of Ginger's halves. Let the cat core muscles have 10 Newton meters of torque. Then the front half acceleration is torque divided by inertia, or 10 divided by 0.025, or 400 radians per second squared. Similarly, the back half is 10 divided by 0.005, or 2,000 radians per second squared. To compute the angular acceleration, or the angular position after constant angular acceleration for a time t, we use position equals a half times acceleration times t squared. So after a time t, the front has moved half of 400, or 200 t squared, clockwise, and the back has moved half of 2,000, or 1,000 t squared, counterclockwise. It makes sense that the back is twisted more than the front, since it has a lower inertia and they both see the same torque. In our big picture, Ginger stopped on a dime now, reversed her paws, then twisted back the other way the same length of time. So by symmetry, the front will then move back 1,000 t squared counterclockwise for a total of 800 counterclockwise. The back will move 200 t squared clockwise for a total of 800 t squared counterclockwise. We do see that both front and back have spun counterclockwise, so at the end, Ginger is not twisted in a corkscrew. At the end of the day, we want Ginger to do half of a turn, going from upside down to right side up for a total distance of 180 degrees, or pi radians. So we need 800 t squared to come out to pi, or t to be the square root of pi over 800, which comes out to about 62 milliseconds. So plugging 62 milliseconds back into our formulas for how far Ginger's halves have traveled, we see that her front and back have each traveled about 3.8 radians one way and 0.7 radians the other way, or about 3.1 radians net, which is about 180 degrees, just as we wanted. So that's good. That's the end of our example. We got Ginger to right herself without twisting herself into a corkscrew. We should note, by the way, that real cats are actually even a bit smarter than Ginger is. They contort themselves so that their front and back halves spin along different axes, which is actually a bit more efficient for the cat, but harder for us to analyze. So we will leave that for another day, and thank you for listening.